Good morning, everybody. Welcome back to Abstract Algebra. Plan for today, we're going to continue our discussion about the symmetric group, as you may recall, is the permutation group on the set of positive integers 1 through n for some n. Next upcoming office hours, I've got my usual office hours on Monday, the hour before class, and from 2 to 3. And as a reminder, homework 4 is now due next Wednesday. And not today. Like I said, I'm just hopelessly behind in grading. I've gotten most of the way through grading homework 2 at this point. You might check. Some of you probably have comments. Some of you can see your score, some of you cannot because I'm partway done. I'm going to finish those off this weekend. I apologize for being so behind on grade. I don't like it. It's not a nice feeling. But grading isn't fair this semester. So I'll get homework 2's done this weekend, and hopefully homework 3's I'll be working on next week. Exam 1, as a reminder, will be assigned next Wednesday-ish, plus or minus a day, might be Tuesday, and will be due the following Wednesday. And as a reminder, you are allowed a partner to work with. Meaning you can work with one other. You can work with another person and discuss the exam together. And none of this nonsense where person A is going to partner with person B. Person B is going to partner with person C. Person C is going to partner with person D. Don't cheese it, or you will regret it. In a vague, unspecified way. A couple things before we get started today. First of all, Parents' Weekend. There's no freshman here. Y'all know the drill for Parents' Weekend. I'm not going to be available on Parents' Weekend to meet with your parents for a variety of reasons, mainly boiling down to it sounds suicide. So if you know your parents coming to Parents' Weekend, please let them know I will not be available for in-person meetings. But if they would like to meet with me, I would be happy to set up a virtual meeting with them. So just have tell me if you want if your parent would like to meet with me over Parents' Weekend, and we will make something happen. Cool. Let's see. What other announcements? What did the mathematical acorn say on the day it grew up? On the day it grew up, the mathematical acorn said G on the tree. Okay, before I get back to talking about the symmetric group, I want to go through a quick little theorem. You do not need to write this one down. I just want to make a point of something I've been noticing while grading homework 2s. Here's the theorem. If x is even, then x squared is even. Assuming x is an integer. So here's my proof. Let x be even. X equals 2n. X squared equals 2n quantity squared. X squared equals 4n squared. X squared equals 2 times 2n squared. X squared is even since it is a multiple of 2. I want you to take a minute or two. If you want, you can talk to your neighbor about it. What is wrong with this proof? Take a minute and think about it, and then we will see if we can construct a better proof together. And when I say bad, I don't mean like it's complete garbage. It's like there's something missing from it. I'll put it that way.
Yeah, I was going to say.
Do you know?
I'm not sure.
Oh, wow.
You're right, I didn't define it, but that was what I was looking for.
Is it
Is
just
it an
one thing?
instantiation problem? Like,
If there's one specific thing I'm looking for that may be occurring multiple times, or that may be missing multiple times.
Okay.
Just like same thing as when the equations.
Does anybody have any thoughts about this? Like, what can we do that would make this, that would kind of improve this, make it improve the flow, so to speak?
I don't know what it's called, but do you need the little arrow thing before each equality? Shows that they have it.
Like that?
Yeah.
Indeed. Yeah, so it doesn't need to be that specific arrow or anything, but there needs to be some sort of way to connect the individual lines. Like, let x be even. X equals 2n for some integer n. X squared equals 2n squared. All of this is fine and dandy and important parts in the proof, but it's important to have something like then. Like, so have some way of connecting each line to the line that comes before it. And it may feel a little bit pedantic, like it's not changing any of the mathematical essence of what's going on here. But the fact that we are sort of including like then x equals 2n, then x squared equals 2n quantity squared, which implies x squared equals 4n squared, which implies x squared equals 2 times 2n squared, thus x squared is even since it is a multiple of 2.
if you left the x squared off every line, except for the first time you used x squared, and just wrote like, say, equals 4n squared equals 2 times 2n squared, is that enough of a?
Indeed. Good job predicting my next question to you all. Yeah, another way we could have done this is by just saying x squared equals 2n quantity squared, which equals 4n squared, which is equal to 2 times 2n squared. That I would consider to be a single equation, so you don't need thens before the equal signs, because it's all like the same equation. But when you're going equation like that, you would need to have some sort of then or some arrows to indicate like therefore, some way of connecting each line to the one before it. Whereas if you just leave off the x squares and just say this equals that equals that equals that, even though it's not written that way, I would consider this mathematically to just be a single line of your proof. Like, then x squared equals 2n quantity squared, which is equal to 4n squared, which is equal to 2 times 2n squared. But yeah, something like that would also be perfectly fine here. I bring this up because I noticed in a lot of the homework twos I've been grading, like a lot of you have kind of been just like having giant strings of equations without any sort of kind of words in the middle to sort of go from one line to the next. And it is a relatively minor thing, but it's enough of you are doing this that I thought I'd kind of share it with the class. And I'm not going to take off like 10 points if you do it 10 times or anything, at least not yet. But because I totally get that homework 2 is kind of like your first like really proof-based homework, and that there's kind of the first homework where I ask you to write some proofs. But that is something to keep in mind. Is you need to be able to it needs to be clear how you get from one line of your proof to the next, even if it's just something as simple as saying then or thus or therefore, which are all different ways of saying this line being true implies the next line has to be true. It needs to kind of, it adds a sort of logical flow to what's going on. Any questions or comments about any of that? Just something to think about as far as a way to kind of improve your proof writing in the future. And if you did, and if you were one of the people who did this, you were one of many. Don't feel bad about it. Unless this is like your third proof-based writing course, in which case you should feel ashamed. But no. Okay, that's all I had to say about that. All right, let's get back to symmetric group. So, decided not to rewrite the proof and just do it in place. So you may recall, last time we talked about the symmetric group, Sn, as being the permutation group on the set of integers from 1 to n. And in particular, we were looking at the elements in S3, which, as you all determined in Wednesday, were the identity element, the permutation that just maps 1, 2, and 3 to themselves individually, Permutation that swaps 1 and 2, but leaves 3 alone. Permutation that swaps 1 and 3, leaves 2 alone. Permutation that swaps 2 and 3, leaves 1 alone. The permutation that maps 1 to 2, 2 to 3, and 3 back to 1. And finally, the permutation that maps 1 to 3, 3 to 2, and 2 back to 1. And again, the way you kind of read each of these as a function is if you look at these individual, like this bottom one here, each number maps to the one that comes after it in the notation. So 1 is mapping to 3, 3 is mapping to 2, and then the last one just maps back to the first one. And we also said that for something like 1, 3, this cycle, or this element, if a number isn't mentioned, then it's just assumed that that number maps to itself. So this one maps 1 to 3, 3 back to 1, and 2, and would map the number 2 just back to the same number 2. And we kind of left off at the end of class. We were looking at what would happen if you tried to multiply some of these elements together. Keeping in mind that the group operation in any permutation group, including in the symmetric group, S3, is going to be composition of functions. So, as an example, if we wanted to take 1, 3 and do the group operation with 1, 2, 3, we're going to be looking at the permutation that comes from doing basically one of these composed with the other. Think about this as being like if this is our function f and this is our function g, then multiplying those two permutations together is like taking the composition of them, taking like an f composed with g of x type thing. Okay. So I want to write this. I want to be able to find out if we multiplied the permutation swapping 1 and 3, and this one sending 1 to 2, 2 to 3, and 3 to 1. Which of these 6 elements in S3 are we going to get when we multiply these together? So here's how it works. One kind of nice way you can check out where each of these is going to map 1, 2, and 3 is by just doing one of them, seeing where one maps to, 2 maps to, 3rd maps to under the first permutation, and then see kind of where do those numbers then map to under the second permutation, and then you can sort of follow the arrows in the diagram, so to speak. So, if we were multiplying these together and doing these as a permutation, where is the first permutation going to map 1? Elaine?
Is it going to be to 2?
Dang it, you didn't fall for it. Yes, it is actually going to map to 2. But Dr. Gerstle, the first one says 1 goes to 3. This is, in the symmetric group, you have to think about multiplying things as being just like the dihedral group in which you actually have to read the permutations from right to left. It's because, for the same reason that when you compose two functions, f composed with g of x, the first thing you're doing is g of x, and then you're doing f of x. You actually read the functions off going from right to left. So just like in the dihedral group when we were talking about, rs means do s and then do r, here the permutation 1, 3, 1, 2, 3 means do the second permutation 1, 2, 3 first, and then do 1, 3. So yes, Elaine, you are absolutely correct. You did not fall for my trap. 1 does go map to 2 first. 2 is going to map to 3, and 3 is going to map to 1. And then, so this is going to be our first permutation, maps 1 to 2, 2 to 3, 3 to 1. Now we can do our second permutation and see where that maps all those numbers. Where's the second permutation going to map 1? Dave, what do you think?
3.
I'm purposely going to stare right between the two gates. Last time I taught abstract algebra, I had 3 students named Emma in the class, and I would frequently do that. I just look at the board and say, Emma, what do you think? And they all like, and then I turn around, they're all looking at each other like, what? Who's How do you?
3.
Let's see, 1 is going to map to 3. Where's 3 going to map to?
What?
And where is 2 going to map to? Since 2 is not mentioned in the second permutation, i.e. the leftmost one, 2 is going to map to itself. And so now we can sort of see what is everything being mapped to under the composition of the 2 permutations. Because 1 is going to map to 2, which is going to map to 2. So 1's going to map to 2 in the composition. 2 is going to map to 3, which is going to map back to 1. And 3 is going to map to 1, which then gets mapped back to 3. So we don't need to write 3 down because it's just mapping to itself. So it turns out the product of 1, 3 with 1, 2, 3 ends up just being 1, 2. Dr. Gerstel, what happens if we multiply 1, 2, 3 and 1, 3 together? That's a good question. Typically, I find the arrow diagram helpful to start evaluating products of these elements in Sn. I find it helpful to draw the arrow diagrams to start out, but if you're good at it, once you get more skill, once you've done some of these, it's a little easier to maybe just read off, go from right to left and see where is every element mapping. So starting off, we know 1 is going to map to 3 in the first permutation. In the second permutation, 3 is going to map back to 1, so 1's going to map to itself. 2 maps to itself here, which maps to 3 in the second permutation. So in the composition, 2 is going to map to 3. And finally, 3 is going to map to 1 in the first permutation, which in the second permutation will map to 2. So 3 is going to map to 2 overall. I just kind of did out loud in my head what the same thing as the arrow diagram I just drew earlier. Saying things like, oh, 1's going to map to 3, which maps back to 1. 2 just maps to itself and then maps to 3. 3 maps to 1, maps to 2. And I could have gotten this the same way. You don't necessarily need to draw the arrow diagrams every time if you're comfortable doing it in your head. But while you're doing this at first, it might be helpful to draw these arrow diagrams just to see where is everything mapping. What did we just show about S3? S3 is not an abelian group. Because we just actually took the same 2 elements in S3 and composed them in different orders. And composing them 1, 3 first, we got 1, 2. Putting 1, 2, 3 first, we got 2, 3. So since these are not equal, that tells us S3 is not abelian. Actually, we just proved more than that. We just proved SK is never going to be abelian as long as K is greater than or equal to 3. Because we can think about 1, 2, 3 and 1, 3 as being permutations in larger degree SK, so like an S4 and S5. It's just that 1, 2, 3, this cycle, as an element of, say, S5, technically is, okay, it's the permutation that maps 1 to 2, 2 to 3, 3 to 1, 4 to 4, and 5 to 5. Because if it's not mentioned, we're assuming it maps a number to itself. So each of these permutations we can consider being elements in S4, S5, etc., and just mapping all the other the integers greater than 3 back to themselves. And so that actually tells us right here that Sn is not going to be an abelian group for n greater than or equal to 3. And yes, Nick, S1 and S2 are abelian, but they're also very boring groups that have only 1 or 2 elements in them respectively.
Yeah, yeah.
He's asking me about this stuff. And it turns out all groups with 1 or 2 elements in them are abelian. But you already know that from homework 4. Any questions about how to take the product of 2 things? For some strange reason, I put in the packet, let's draw a Cayley table for S3. I kind of don't want to do that because that's just big and long. I mean, it's a 6x6 table. So my solutions that I'm posting online are going to have the Cayley table in them, and you are welcome to look at that. And it's good practice if you want to try constructing the Cayley table on your own. So the order of S1 is going to be 1. The order of S2 is going to be 2. The order of S3 is 6. S1 permutations of the number 1, well, there's only a single one, which is the identity map. Only a single or 2 permutations on the set containing 1 and 2, the function that just, the identity map and the function that swaps the two numbers. S3 has 6 elements. I'll go ahead and tell you S4 has 24 elements in it. Anyone notice a pattern that they'd like to propose for what they think the order of Sn is going to be?
N! Exclamation.
N! Super excited N. So, I'm guessing you were trying to say n factorial in your own excited way. And that is correct. The order of Sn is n factorial. If you haven't seen this notation before, if you have a number like n, you have a number like n, yes. That's followed by an exclamation point. That's the factorial function. That just basically means it's going to be n times n minus 1 times n minus 2 all the way down. Basically, we multiply all the integers from 1 up to n. So 1 factorial is just 1, 2 factorial is 1 times 2 is 2, 3 factorial is 1 times 2 times 3 is 6, 4 factorial is 1 times 2 times 3 times 4 is 24. Order of S5 would be 120, order of S6 would be 720, and then it just keeps getting bigger and bigger from there. Why do we know that the order of Sn is n factorial? Turns out it's not actually that it's not actually too bad to actually go and prove this fact. Proof just basically says, let's say given the set 1, 2, 3, all the way up to n, if we wanted to make a permutation in Sn, how many different elements can one map to potentially under a permutation, for a single permutation in Sn? I would say n, because one could map to itself. Yeah. N could map to one could map to any one of these n things. So we could say for any, let's say sigma and Sn, 1 can map to any of the n elements. There's no restrictions on how a permutation of this set, where 1 could map to. Once you've chosen where 1 maps to, how many of the remaining elements can 2 potentially map to? N minus 1. It can map to 2 can map to anything in this set except for what 1 maps to. 1 and 2 can't map to the same thing because then our function would not be 1 to 1. So 2 can map to n minus 1 elements. Everything except what 1 mapped to. How many elements then can 3 map to? N minus 2. If 3 can map to anything except for what 1 and 2 individually map to. Dot, dot, dot. And then at the end, once you see what n maps to, well, there's only one possible thing left in the set that n could map to, and still get something that is 1 to 1. Then n can map to 1 element. And then, so how many different choices are there to be had? there's n choices for 1, n minus 1 choices for 2, n minus 2 choices for 3, etc., etc. It's going to be n factorial possibilities altogether. So you just multiply the number of possibilities for 1 by the number of possibilities for 2, and so on. Thus, there are n times n minus 1 times n minus 2, 1 equals n factorial possibilities for sigma. So Sn is always going to have n factorial elements. Questions or comments? Okay, go ahead and flip the page. And what I would like for you all to do is take a couple minutes, and I want you to evaluate a few products in S4 on your own. What I would like for you to look at is I want you to try and multiply these cycles in S4. I'm going to multiply 1, 2 by 2, 4. 1, 2, 3, 4 by 1, 4, 3, 2. And 1, 2 by 3, 4. Go ahead, take a couple minutes and see what happens if you were to multiply these things together in S4. In particular, which elements of S4 are these products going to result in? Should probably space them out a little bit more so you have room to write. As always, you can talk to your neighbor or flag me down if you have any questions. If you want to do it using the arrow method, you are certainly welcome to. If you want to try and figure out in your head where things map to, that you can do that too. If you feel like you have an answer, go ahead and if you feel comfortable doing so, see if your neighbors agree with you.
I got the identity for the second one. Okay, for the third one, I just got 1, 2, 3, 4.
I didn't have
Wait,
some.
what?
I should write it down.
Or the third
So
one, like
fancy
the
about it, probably shouldn't.
Oh, okay. Well, so 3 would map to 4, and then 4 would map to itself. 4. Yeah. So the 4, and then 4 maps to 3, which would also map to itself. So it's the same as the previous one.
Dave, I can tell you've done a lot of theater here because your voice really carries.
Oh, thanks.
So I can hear lots of conversations set up indistinctly, and I can hear your voice very clearly.
I guess that's good.
Did you get to the first one? How many did we forgot?
4.2. I think I messed up. I did the 2. 2 maps to 4, maps to itself. 4 maps to 2, maps to 1. Wait, just the third one.
So 1 would map to itself, which would map to 2. I just think it's interesting that this
Uh,
one is better than the last one.
Would you
Okay.
probably support 412?
Quite interesting.
I guess.
And that's gonna be our way with S four, it is a little bit differently than this.
Yeah.
Option.
That was not a good idea on your part.
Yeah, I don't know about this. That one, no, right.
Very careful.
What the heck?
Semicolon.
Yeah,
right?
yeah, exactly.
Sounds like
Same
that. Yeah, the last one is actually, I think, the trickiest of the
Yeah,
three.
I think.
We're gonna talk about that one.
Exact same thing.
You're right to suspect that something's up.
I wonder if it works the other way with Nebula. Interesting. See.
Gonna take a few more seconds and then we'll come back together and talk about these.
What'd you get for the last one?
Is that possible? Is that a thing? I think so. Okay. Here, one is not to one. Which would match to two. Or two not to two. Which would match to right? Three would match to four. Which would match to
What's all people gonna watch these videos? You're just gonna see me like looking out into space and then just like taking a step backwards. You're saying
Does
what?
that give us like the big set, like 2, 1, 4, 3?
Oh, I should say.
Oh, I should make an announcement.
No, because
No, you're not in the video. You don't
we're
work.
on the 2, 1.
Hi, people watching the videos. You all are great, and please let me know if you have any questions or want to ask anything about any of this. Happy to talk to you. You all are awesome. Stay safe, please. Stay awesome.
I think you can hear me though.
Probably, but all right. Let's come back together and talk about these three products. Anybody like to share what they got when they multiplied 1, 2 by 2, 4? Yes, Becca.
1, 2, 4.
Becca got 1, 2, 4.
Yes.
Let's see. Becca proposes 1, 2, 4. When I do this, I got, let's see, 4 maps to 2, which maps to 1. So 4 is going to map to 1. 1 is going to map to itself and then to 2. 2 is going to map to 4, which maps back to 4. No, sorry, Becca, I got 4, 1, 2. Well, there we go. Move on. Just a little reminder that given each of these elements, there's oftentimes multiple equally valid ways to write it. How about 1, 2, 3, 4 times 1, 4, 3, 2? Or a few people say the answer to this one. Well,
Just the identity on
that's going to give us the identity. Because 1 will map to 4, which will map back to 1. 4 maps to 3, which maps back to 4. 3 maps to 2, which maps back to 3. 2 maps to 1, which maps back to 2. Yeah, so it turns out this last one is the identity element. By the way, what does that tell us about the relationship between 1, 2, 3, 4 and 1, 4, 3, 2?
They're inverses.
Indeed. Yeah, if we take the inverse of 1, 2, 3, 4, we're going to get 1, 4, 3, 2. And we can even say that in general, 1, 2, 3, or let's not do it with specific numbers. If we have a single cycle like A, B, C up to K, and take the inverse, I'd like to take a stab as to how we could possibly write that inverse out.
Just writing it backwards?
It's writing the same cycle but backwards. Yeah. So it's going to be K, dot, 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 C, B, K. Or you can start it with A and then go A, K, J, I, H. I know the alphabet backwards. And then do D. The order in which you write where you start doesn't matter, but the order does matter after that point. What about this one? 1, 2 followed by 3, 4. Right?
I got that 1 maps to 2 and 3 maps to 4 still, so I had to leave them separate. I don't know how you write that.
So you don't know how to, so you just got the doing this times this gives you that times that?
Yes, precisely.
Correct! This one is insidious in that it can't actually be simplified at all. because there is no way to write using a single cycle the permutation that swaps 1 and 2 and swaps 3 and 4. You have to write it out using multiple cycles like this. I like to think about it as, if I were to ask, who do I want to pick on? Oh, Peter put his hat down, so I'll pick on him. Here, if I were to tell you to add together 1 and square root of 3, what would you get?
1 plus the square root of 3.
Yes, but what is that?
It's an irrational number, so you can't.
You can't really simplify it any more than just saying it's 1 plus square root of 3.
1 plus or minus the square root.
No, just 1 plus. So there's like a 1 plus square root of 3. You can't like simplify that down. There's not like a simple way of just combining 1 and square root of 3 into something nice. Same goes here. 1, 2, and 3, 4. You can't really combine those into a single cycle. And if you look at the question at the top of the page, how does S4 differ from S3? S4 differs from S3 in that S4 and higher are going to have some elements that look like this. Single elements in Sn that can't be written as a single cycle. So I'll just say S4 plus has elements that can't be written as a single cycle, unlike in S3. And the reason why S3, everything can be written as a single cycle is because in order to have something that can't be written as a single cycle, it has to be permuting 4 separate elements. The sort of 1, 2 here, and 3 and 4 all have to map to different things. You can't just permute 3 different elements in any way that can't be just a single cycle. So, but S4, S5, S6 all have things that look like this. In S4, for instance, we have 1, 2, 3, 4. Can anybody think of another permutation in S4 that can't be written as a single cycle? Right? 1, 3, 2, 4. Any others? Okay. 1, 4, 3, 2. I'm being a rebel, right? 3, 2 instead of 2, 3. And that's all of them, turns out. The ones that swap 1 and 4 and 2 and 3, the one that swaps 1, 3 and 2 and 4, and the one that swaps 1, 4 and 2 and 3. S5 and up, there's a lot more of these things. Sort of things that show up. Once you get to like S6, you can even have things that have to be written as products of 3 separate cycles. Like 1, 2, 3, 4, 5, 6, for instance. Yeah, Nick?
So in S3, we kind of, when we have like if you have 1, 2 in S3, then isn't there an implied 3 as well? Is that not considered a cycle if it's just a single element? Because isn't, like in S3, isn't it 1, 2 times 3?
Technically, yes. But we don't write it, so I don't think about it. But you're right. Technically, when we write something like in S3, or like this in S4, technically, oh, it's 4, 1, 2 times a single cycle that just that maps 3 to itself. That is implied, but we often just don't think about including it at all, because the absence of the number 3, has this hidden implication to it, of mapping to itself. Okay. Any other questions about how Sn works in general? So, last thing I want to talk about in Sn for today is a sneaky subgroup of Sn called An, the alternating group. So, we flip the page, I finally defined what a cycle is. So an n cycle is just going to be one of these single things, like things in parentheses. It just has n elements popping up in it. And turns out that in studying Sn, what's often interesting is the study of 2 cycles. And no, sadly, no algebraists tend to use the word bicycle to refer to cycles of 2 elements or 2 cycles. And 1 cycles are just not referred to at all, Nick. They're not called unicycles. Tricycles. But here's going to be my goal. I'm going to write, what did I say? 1, 2, 3, 4 as a product of 2 cycles. And I don't know, S10. Fun fact, it turns out any permutation in Sn you can always write as a product of 2 cycles, unless you're in S1, in which case there are no 2 cycles. That's not weird. So, it turns out there's actually a nice way to always take any single cycle, like 1, 2, 3, 4, and break it up into 2 cycles. Here it is. You take the first element, 1, and you map it to the last element in the 2 cycle. Then you take the first element again, and you map it to the second to last element. And then you keep going down the line, 1, 2, until you get back to the beginning. So it turns out 1, 2, 3, 4 can be written as 1, 4, 1, 3, 1, 2. Because this is going to map 1 is going to map to 2, which maps to 2, which maps to 2. 2 is going to map to 1, which maps to 3, which maps to 3. 3 is going to map to 3, which maps to 1, which maps to 4. And 4 is going to map to 4, is going to map to 4, is going to map to 1. And in general, and if I want to be cheeky, I can add on a couple more like that. Because 5 is going to map to 6, because 1, 2, 3, 4 are all going to behave the same. If I added a 5, 6 to the beginning and end. 5 is going to map to 6, maps to 6, maps to 6, maps to 6, maps back to 5. So 5 maps to itself. 6 is going to map to 5, maps to 5, maps to 5, maps to 5, maps to 6. 6 maps to itself. You can always just tack on some 2 cycles, including elements that don't matter like that at the beginning and end, or in the middle. Here's a fun fact. Given some element, sigma and Sn, it turns out that if we can write it using an even number of 2 cycles, then every way of writing it using 2 cycles will be using an even number of them. So sigma and Sn we can call an even permutation if sigma can be written using an even number of 2 cycles. And an odd permutation, we can write sigma using an odd number of 2 cycles. And being able to classify the permutation as being even or odd is going to be very useful for us. So let's take this one. 1, 2, 3, 4. Is that going to be an even permutation or an odd permutation? Meaning, if we were to try and write 1, 2, 3, 4 using just 2 cycles, can we do it using an even number of 2 cycles? Or an odd number of 2 cycles? Ready? 1, 2, 3, 4, 5, 2 cycles. Yep, that one's going to be an odd. 1, 2, 3, 4 is going to fall into this odd category because we can write it using an odd number of 2 cycles. We could even put a 5, 6. And we could put it at the start. We could double it if we wanted to. And here's the cool thing about even and odd permutations. We can write 1, 2, 3, 4 using 3 permutations, 5 permutations, 7 permutations, 9, 11, 13, etc. Or 2 cycles. I could find a way to write 1, 2, 3, 4 using any of those number of 2 cycles. I could just add 5, 6, 5, 6 to the start enough times. But there is no way to write 1, 2, 3, 4 using an even number of 2 cycles. What if I did a 3 cycle? 1, 2, 3. Is that going to be an even permutation or an odd permutation? Right.
Could be even,
Prove it.
1, 3, 1, 2.
Checks out. So 1, 2, 3 is going to be an example of an even permutation, because we could write it as 1, 3, 1, 2, 5, 7, 8, 99, 8, 99, 5, 7. This is true. So everybody good with 1, 2, 3 being an even permutation and 1, 2, 3, 4 being an odd permutation? Or is there something nonsensical about that?
Does it have something to do with the amount of elements in it? Because it looks like the one with 4 elements gave us an odd, and the one with 3 gave us an even.
How about that? Yeah, so it turns out if you have an n cycle, an n cycle will be even if n is odd, and an n cycle is odd if n is even. Which makes no intuitive sense, but it comes down to the fact that when we classify a permutation as being even or odd, we're not referring to the number n of elements that it's sending to other things. We're referring to the ways in which we can write it as a product of 2 cycles. And it turns out that 1, 2, 3, or let's say A, B, C, up to some n, we can always write using n plus 1 2 cycles. If it has n elements in it, then it can be written using n plus 1 2 cycles. And so if n plus 1 is even, then the permutation will be even. If n plus 1 is odd, then the permutation will be odd. But n plus 1 being even means n is odd, and n plus 1 being odd means that n is even. And so it doesn't make that much, it really doesn't make much intuitive sense, but even permutations, single cycles at least, will be even if if they're have an odd number of elements in them, and vice versa. Don't be the one to mistake even permutation as being an even number of elements within it, because you will be sad and regret. Yeah,
Isn't it also, you can just do it with n minus 1, right?
Nope. Oh, yes, that's what I meant, n minus 1. Look. You're right, you can do it with n minus 1 2 cycles, but you can't do it with n minus 3. And so you need at least n minus 1. Sorry, I miscounted something in my head. I was the person who made the mistake. I said, you shouldn't make. Oh, embarrassing. Yes, Nick?
But you could go the other direction, like you could do it with n plus 1 2 cycles
Yes.
or n plus 3.
If you can write something as a product of n 2 cycles, you can always do it using n plus 2, n plus 4, n plus 6, etc., just by tacking on the same 2 cycle twice to the beginning or end, however many times you would like. All right, homework for next time. Surprise, there's homework for Monday. Think about the last page's packet. You don't need to write anything up. We're going to talk about it, but does the set of all even permutations form a subgroup of Sn? And/or does the set of all odd permutations form a subgroup of Sn? Something to think about. We will discuss this on Monday, and then we're going to discuss our next major topic, which is isomorphisms. Have a good weekend, everybody. See y'all on Monday.
What are you doing right now?